Nuclear fusion is a nuclear reaction occurring in stars. Two or more atomic nuclei collide at very high speed and join to form a new type of atomic nucleus. For example, three hydrogens could combine to create a lithium atom. However, the simplest and most commonly occurring reaction would be two hydrogen nuclei combining to create a helium nucleus. The most important product of this reaction is, of course, energy. This energy is given off because the helium nucleus has slightly less mass than the reactants. This loss in mass is converted into energy. This energy is given off as radiation and as photons of light. This follows Einstein's law, E equals mc squared. Isotopes of hydrogen and helium combine to have slightly different products and can produce much greater levels of energy. These reactions provide the energy for our Sun and other stars. Fusion reactions have an activation energy called the Coulomb barrier. If this amount of energy is not met in the speed of the colliding atoms, the reaction will not occur. In theory, it's possible to shoot some energy at a hydrogen and get even more energy back. The trouble is, the scientific and technical hurdles ahead are still enormous. In fact, we still don't have a full grasp of what the hurdles might be. Still, the potential payoff is so massive that countries have sunk billions of dollars into fusion research. It turns out that it's very hard to reach the Coulomb barrier. The Sun combines huge pressures and temperatures in order to accomplish this. Seeing as we do not have the technology to create these pressures, we would need to make it even hotter than the Sun does. By doing this, we would end up turning the hydrogen or helium gas into a plasma. That is, if we could actually accomplish to create these temperatures. Stars are hot bodies of glowing gas that start their life in nebulae. They vary in size, mass and temperature, diameters ranging from 450 times smaller to over 1,000 times larger than that of our Sun. Masses range from a 20th to over 50 solar masses, and surface temperature can range from 3,000 degrees Celsius to over 50,000 degrees Celsius. The colour of a star is determined by its temperature. The hottest stars are blue and the coolest stars are red. The Sun has a surface temperature of 5,500 degrees Celsius. Its colour appears yellow. The energy produced by a star is by nuclear fusion in the star's core. Stars can be plotted on a graph using the Hertzsprung-Russell diagram. On the axes, there are luminosity and temperature. When stars are plotted, there are four main groups that emerge. The main sequence stars contain stars that are producing energy through hydrogen fusion reactions. The giants are stars that are very hot and have very large masses, yet are not as bright as some other stars of this temperature. White dwarfs are much smaller, dimmer, and cooler than the other stars. Finally, the hottest and brightest of them all, the supergiants, which are also incredibly massive. Stellar evolution begins with the gravitational collapse of a giant molecular cloud, forming a protostar. The temperature increases due to the compression of the protostar. When the temperature exceeds 10 million Kelvin, hydrogen fusion reactions start. This means that the star becomes a main sequence star. Depending on the mass of the star, it will either become a red giant or a red supergiant. This happens when the hydrogen fuel for fusion runs out. Red giants become white dwarfs, shedding their outer layers and leaving a small, dense core behind. Often only the size of the Earth, but with masses similar to that of the Sun. When the star completely cools down, it becomes a black dwarf. Red supergiants take a different course. They will often suffer gravitational collapse, leading to a supernova explosion. an event creating many new elements and releasing incredibly large amounts of energy. The remains of a supernova will either produce a neutron star, an extremely dense star, often only 10 kilometers across, but with the mass several times that of the Sun. Remains with more mass will form a black hole, in which the gravitational force becomes so much that it collapses in on itself and forms a point of infinite density. At present, 116 elements are known, and only about 90 of these occur naturally. In the Big Bang, only the lightest elements were formed, hydrogen and helium. The other elements found in nature were created in nuclear reactions in stars and in huge stellar explosions known as supernovae. Stars fuse elemental hydrogen into helium in their cores. Two atoms of hydrogen are combined in a series of steps to create helium. These reactions continue to create lithium and beryllium. Red giants then create carbon atoms. More massive stars begin a further series of nuclear burning or reaction stages. The elements formed in these stages range from oxygen to iron. As the mass of the element increases, more energy, i.e. pressure and heat, is needed to create it. From all these levels of energy, different elements are produced, and these energy levels can be found in different types and heats of stars.
So fusion's the main energy source in the universe. It's obviously the energy of the stars, the energy of our sun. It's what supports most life on Earth, of course. It's a bit surprising, given it's the main energy source in the universe. It's not used here on Earth, and of course that's what we're trying to do, bring fusion here on Earth. The estimates of how much work there is to do to develop fusion from beginning to end is that there's roughly $50 billion worth of work. We've probably done maybe 5 to 10 billion of that so far, so there's another roughly 40 billion worth to go. It's not really a time thing, it's an expenditure thing or a research thing, how much work. So there's still about that amount of work to go. That'll probably take us another 30 years or so at the present rate of expenditure. So we've mostly got on top of the scientific issues. There's a lot of engineering challenges, but the main ones are handling the huge amounts of power that we'll be able to produce over the next 10 or 20 years. A particular problem is the cost of superconducting magnets. And also we're working hard to develop better maintenance schemes for a power station.